BB2 and once again issue a show IP mroute. And let's see what this output is telling us. Notice that we now have a star comma G entry in addition to an S comma G entry. On the star comma G entry, the D flag is telling us that we're running in dense mode. But on this S comma G entry, the source is 3.3.3.3. That's router BB1. And the G, the group, is 239.1.1.1. Notice the P and the T flags as well. The P flag lets us know that we have pruned this router off of the multicast distribution tree. If we look at the incoming interface, we see that the incoming interface is serial 0/0.1, and the outgoing interface is serial 0/0.2. This is seen in what's called the OIL, the outgoing interface list. The outgoing interface is leaving BB2 destined for R1. However, this link has been pruned off because this router is not part of the shortest path tree, or the SPT. And by the way, you might wonder why we have both a star comma G entry as well as an S comma G entry for the 239.1.1.1 group. Here's the rule. Whenever we have an S comma G entry in our IP multicast routing table, we always have a parent star comma G entry. Let's go over to router R1 and check out its multicast state. Let's do a show IP mroute. Show IP mroute. We now have an S comma G entry on router R1. It shows that we're coming into router R1 on serial 0/0.1, which means that we're coming in directly from router BB1. Our OIL, our outgoing interface list, shows that we're sending traffic out of Fast Ethernet 0/0, and also serial 0/0.2, which goes up to BB2, but you'll notice that link has been pruned off. BB2 does not have any receivers for this group, so that link of the tree has been pruned off. Also notice the flag on the S comma G entry. It's the T flag. The T flag indicates that we are currently using the shortest path tree, or the SPT. Also notice that in addition to the D, the dense mode flag, we pointed this out earlier, in addition to the dense mode flag on the star comma G entry, we also have the C flag. As a reminder, this indicates that we have a receiver for this group connected to this router. In our example, router R2 is acting as the receiver, and it is directly attached to router R1. But as we discussed earlier, we're not big fans of PIM dense mode usually. We would much rather use PIM sparse mode. Here's how we can make that work. Let's statically configure our routers with the IP address of a rendezvous point, or of an RP as we call it. Let's say that we want to make this IP address, 10.1.1.2, the serial 0/0.1 interface on router BB2. Let's say that we want to make that the address of our rendezvous point. Let's tell all the routers about that address. We'll begin over on router BB2. In global configuration mode, let's say IP PIM RP-address, and we give that IP address, 10.1.1.2. We give the same command for the remaining routers. On BB1, we go into global config and we say IP PIM RP-address 10.1.1.2. We do the same thing on router R1. In global configuration mode, we say IP PIM RP-address 10.1.1.2. And finally, on router R2, in global configuration mode, we say IP PIM RP-address 10.1.1.2. Let's once again generate some traffic for this multicast group by issuing a ping from router BB1. On router BB1, let's once again say ping 239.1.1.1, and let's check out our multicast state on routers BB2 and on R1. First, on BB2, let's do a show IP mroute once again. And notice that the OIL for the S comma G entry indicates that we are forwarding traffic out of serial 0/0.2. That would be the case initially when we first start sending traffic from BB1 over to BB2 and then down to R1, but subsequent traffic would cause R1 to form a shortest path tree with BB1. So let's do this. Let's go back and issue additional traffic. Let's go back over to router BB1 and let's do a ping. And we will go to 239.1.1.1, but this time let's send 5. We'll send 5 different multicast packets. And by sending multiple multicast packets, not only will the first packet go via the rendezvous point, via router BB2, we will then allow the shortest path tree switchover to happen. Let's go back over to router BB2 and once again check out our multicast state. Let's do a show IP mroute. And this time, notice that the OIL for the S, G entry, notice that the outgoing interface list is null. So there was no flooding and pruning behavior. In the star, G entry, we see the S flag set. This indicates that we are running in sparse mode. We also see that both the star, G and the S, G entries, they indicate that we have a rendezvous point IP address of 10.1.1.2. And again, the reason that traffic is not flowing through this RP is because SPT switchover has already occurred. That's why in our previous issuing of this command, when we sent a single packet, that single packet was indeed forwarded from BB1 to BB2, the rendezvous point, and then down to R1, and then out to R2. However, when we sent additional packets, that allowed SPT switchover to happen so that R2 has the most optimal path between itself and router BB1. Let's go over to router R1 now. On router R1, let's do a show IP mroute. And because SPT switchover has already occurred, the S, G entry indicates that we are using the shortest path tree with its T flag, as we see here. And also check out the star, G entry. The S flag says that we are running in sparse mode. The J flag indicates that we have joined the shortest path tree. And the C flag says, as we indicated before, that this router is directly attached to a receiver, which in this lab is router R2. Well, that's our configuration of IP multicast routing using both dense mode and sparse mode operation. In this lab, we demonstrated IP multicast, and we mentioned a couple of the major protocols used by IP multicast. IGMP, the Internet Group Management Protocol, used between the multicast receiver and the router. In our case, we had an IGMP message going between router R2 acting as the receiver up to router R1 acting as a multicast router. Another protocol that we talked about was PIM, Protocol Independent Multicast. This was a multicast protocol that ran between routers, used for routing multicast packets, and we had 2 modes of operation for PIM, dense mode and sparse mode. Dense mode quickly achieved a shortest path tree, an optimal path between the multicast source and the receiver. However, it did so at the expense of processor and bandwidth overhead for the network. Recall that dense mode used a flooding and pruning behavior where it flooded multicast traffic throughout the topology, and then the routers that did not want to receive that particular multicast traffic, those routers could prune off those links, but that was not a steady state. This flooding and pruning behavior would repeat every 3 minutes. So we were big fans of PIM sparse mode. With PIM sparse mode, we avoided the flooding and pruning behavior because the multicast source router would send traffic directly to a router defined as the rendezvous point, and the rendezvous point router would use a shared tree to propagate multicast traffic out to the receivers. However, the receiver going from its router to the rendezvous point back to the source router, that wasn't particularly optimal. Fortunately, sparse mode supported something called shortest path tree switchover, or SPT switchover, where the router attached to the receiver could send a join message directly up to the multicast source's router. So we could have an optimal path from the multicast source to each of our multicast receivers without necessitating that path go through the rendezvous point, and we accomplished that without the flooding and pruning behavior. That was the big advantage of PIM sparse mode. And coming up in our next lab, and actually for the next 3 labs, we're going to be focusing on IP version 6. What we've dealt with thus far in these labs has been IP version 4, but for the next 3 labs, we will turn our attention to IP version 6, starting off in lab number 13, where we will take a look at how to configure IP version 6 or IPv6 addressing.